Okay, welcome back everybody. So this is a quick demonstration for a two-dimensional versus one-dimensional transport model for concentration. So you have the model parameters here. So mass, dispersion in the x and the y direction. Notice the 1 to 10 ratio here that we adopted. The velocity in meters per day. Again, velocity here will be constant in the x direction, and then time in days. So if I run the model, you can see the 2D models here, evolve in time. So I'm going through time one day at a time, and you can see the plume going from left to right in that 2D aquifer, that very simple model. Notice also here in the plot area that I have a 1D versus a 2D model, and I'm sorry, this is very small to see, but the blue the blue line is the 2D model at y equals 0, so this is the line right here, right? So I'm just taking a slice and plotting that slice in blue here, and then in orange in that plot is the equivalent 1D model. So that means for this model, I use the 1D solution, and there is no second dimension spread, if you will. And that illustrates how the peak, especially the peak, decreases much faster in 2D, again, because there's a second dimension where the mass is, spreading, whereas in the 1D model, you're constrained into a channel, if you will. So you can have that illustration at the bottom here. See how this illustration at the bottom looks exactly like slice through the 2D domain, except again, because the mass now is completely constrained in that narrow band, the peak is much higher. You can see here this is 6 and this is 1, and again this is reflected here in the peak 6, peak 1-ish for the 2D. Okay, so if we keep running it, you can see it goes from left to right. Another important aspect of this model is that, of course, the velocity is completely homogeneous, so it's a constant, it's 2 meters per day throughout the aquifer, and it's only left to right. You remember from our first and second courses that velocity obtained from Darcy's law in heterogeneous aquifers, typically heterogeneous formations, is much more complicated than this, and of course things, the flow would follow patterns that are much more complicated. So this is just to illustrate in Excel, the behavior of a basic assumption model where everything is constant dispersion in the x and y, constant velocity left to right. So of course you get that perfect ellipse, if you will, which would be round if x and y were the same, right? So if I do this, see, and I go back to the initial time is 1 now. Put 10. And then I run it. You can see how now we have a circular spread of the mass, right, instead of that elliptic, because now the dispersion are the same in x and y. So if I go back to, right, and now we have the ellipse because I modified that again to the 1 to 10. Okay, so hopefully this is useful to illustrate the behavior of the advection dispersion model in 1 and 2D. I'll see you in the next video. Bye.